So I posed a question to you at the end of the previous part of this lecture, and so now I'm going to lead you towards the answer. So here are you and your friend Sam standing in a hallway around the corner from each other. And you see these three famous people, Elvis, Psy, and Macklemore, wearing your granddad's clothes, no doubt, walking by. And you note that all three of them walk by. And a moment later, Sam notes that Elvis and Macklemore walk by. And you then compare notes. And this is curious, right? What happened to Psy? Was there a secret trap door that he very stealthily jumped through over here? Is this a hallucination? Maybe Elvis and Macklemore ate Psy? They'd have to have done it very quickly. None of these seem very likely. We tend to believe in a law of conservation of people. People don't just go poof and disappear. And similarly, people don't just appear out of nowhere. So if Sam had seen one more person than you did, that would be pretty strange as well. So, slightly more abstractly, if you and Sam were standing in this hallway and just counting the number of people who go by per hour, if you counted 90 people per hour going past, as long as there are no doorways or other exits here, Sam had better also count 90 people per hour. Otherwise, something strange is happening. So the people current past you must equal the people current past Sam. Well, the same thing has to be true of current, because current is how much charge is passing by, or you could think of it as how many charged particles are passing by it. But as we'll see, we actually think of it as amount of charge. And so the current passing through A here must be the same as the current through B. Now, it's a very persistent and common misconception for students to think that current gets used up somehow in a light bulb. But that would just be exactly like people disappearing walking down the hall. So here's a parable about flow of money. This has nothing to do with charge, of course. So once upon a time, there were these two lands, the mire of debt and the field of credit, separated by the great social chasm. And the field of credit was entirely populated by people called creditors, who had $100 each. And the mire of debt was entirely populated by people called debtors, who had negative $100 each. In other words, they owed $100. And at some time, the national wealth of these two nations was that the mire of debt had 20 people in it, each with negative $100, and so its national wealth was negative $2,000. The field of credit had 12 people in it, and so its national wealth was $1,200. Now, one day, the debtors built a bridge across the great social chasm, and 8 of them crossed the bridge. Now, I should make clear that just because they crossed into the field of credit didn't make them creditors. They still had their $100 of debt that they took with them as they crossed the great social chasm. And so, what was the net effect? Well, the two sides of the chasm had new national wealths. The mire of debt now only had 12 debtors in it with negative $100 each. And so it had negative $1,200. The field of credit had just had 8 people with $100 each of debt arrive, and so its national wealth had fallen to $400. So the overall effect was that $800 had flowed back across the bridge. So the moral of the story is that the money current can be in the opposite direction to the people current, or the money carrier current, because, in modern society, what are people but money carriers? Well, current works just like money flow. The thing with the money flow is that we were talking about the flow of positive money. And so when people with negative money walk one way, the flow of money is in the opposite direction. Now, in a metal where the charge carriers carry negative charge, the same thing happens. In our example of our capacitors causing current to flow in a wire, the electrons are moving around this way. So here's our direction of the electron flow. But since they're carrying negative charge, the direction of what we call current, which is the flow of positive charge, is in the opposite direction. Now, you can get other cases such as an ionic liquid, or a solution. So here's a solution. There's the water, there are the positive ions, there are the negative ions, and if you put an electric field in here, then the negative ions will have a drift velocity in the opposite direction to the electric field, and the positive ions will have a drift velocity in the direction of the E field. And so we'll get two currents, a current due to the positive ions and a current due to the negative ions. But note that both of those currents are in the same direction, and so they add up to a total current pointing in the direction of the E field. We're finally ready to have a formal definition of current. So current is the amount of positive charge flowing through a surface per unit time. And so you can imagine, say, a wire. Here's a piece of wire, and you have a surface that's just a cross-section of the wire, and you have to look at the total amount of charge crossing through that cross-section per unit time. And the current, I, is now defined as the amount of charge per unit time, which tells you what its units must be. The unit is called the ampere, and it must be coulombs per second, just from this. Now, most of the time when we're thinking about circuits, we can think of the wires as if they were just lines, and you don't really need to pay attention to the fact that the current is flowing through a surface. You can think of it as just flowing past a point on the line that you might be imagining the wire to be. But there are other situations where you need to pay more attention to the fact that it is all of the charge flowing through a surface. So, for example, in biology, cells are constantly exchanging ions with their environment, and this leads to flows of charge across the cell membrane. And so if at some time a cell had a net flow of positive charge out through its membrane, that could be caused by positive ions flowing out of the cell or negative ions flowing in, or more likely a combination of both. But the current would have to be defined as the total amount of charge crossing through the whole cell membrane per unit time. And so you have to pay more attention to the fact that it is defined as a flow of charge across a surface. I'm going to close this lecture with what is probably the most useful thing about current when you're doing circuit analysis, and it just uses the thing we've basically been talking about through most of this lecture, which is that charge is conserved. And so if you have a junction where a bunch of wires meet, we don't expect that charge collects there. If it did, the junction would become charged, and it would start exerting electrical forces on things nearby. You don't expect that when you turn on a light or when you turn on your cell phone, that shortly thereafter your hair starts standing on end because of electrical forces being exerted on you by your phone. That just doesn't happen. So charge doesn't collect at junctions in wires. And so that means that the total current into the junction must equal the total current out. However much charge is arriving at the junction, the same amount must be leaving. Otherwise, charge would collect at the junction. So the sum of the currents into the junction has to equal the sum of the currents out. And so, for example, if you had a junction like this, where one wire is splitting into two wires, if there are 5 amperes in here at A and 3 amperes out here at B, we immediately know there have to be 2 amperes flowing out here at C so that the total in equals the total out.